Good morning. No, good afternoon. Okay. Thank you very much. First of all, I would like to express my gratitude to organizers and especially to Francesco. I must admit that we know each other for how much? 14 years, I think. Yes, 14 years, and I want to admit that coming here is always very stimulating, at least for me. I don't know if for Francesco. Okay. Cernik was only once. The topic I'm going to speak today it should be probably interesting for each of us, because I'm going to speak about bonds, and no matter how old we are, probably at a certain moment we will face the problem of joints, bones, maybe tooths. So that means that it is related with our lives. The title is already displayed here, and I'm going to speak about the material which is extremely complex. This material, I mean the tissue, bone tissue, is much more complex than any other materials that man is able to make, to produce. Why we are going to investigate and speak about such materials? There are many reasons. One of the reasons is this, that when we have the tools to model such material and to perform in silico experiments, we can also forecast this, what happens and what might happen in future, and also, for instance, plan the optimal surgery or the medical procedures. How to switch this? Yeah, maybe. Okay. Bone tissue has a very specific characteristic, namely it can recover, in contrast to all other tissues. It can recover to its initial state after injury or after surgery. What means that that it has the ability to modify itself. Even in such difficult cases like that one, it was the bone which was broken into 21 pieces, and after several months it recovered completely, except of one detail. Due to the fact that the person did not walk, there was very low mechanical loading, what causes osteoporosis. That means that changes with osteoporosis we call normally among the doctors, medical doctors, they say osteoporosis means less bone in bone. That means more porosity and weaker bone. So the bone recovered, but unfortunately the person had to exercise for next several months to reach the necessary strength of such bone, of her bone. This is again another example of hip joint which was replaced by the endoprosthesis. And again, even with such a serious surgery, it's really very serious. Since I work in the hospital also, I saw such surgeries. It's really bloody and terrible. So after such surgery, a person can behave almost normally. In order to speak about modeling of bone, first I have to discuss some, say, basic characteristics. So first of all, we should say that bone has very complex microstructure, and it doesn't matter if we use magnification glass or optical microscope, or maybe electron microscope, or maybe even atomic force microscope. We always see very complex picture. So, as I already said, we have very complex geometry. We have complex microstructure. We have very complex microstructure. We even have very complex nanostructure. Why this is? Why we have such situation? This is difficult to answer this question, but anyway. Since bone plays very important role in our organism, it has several very important functions. I will not discuss them because my colleagues will discuss today afternoon in details these matters. But at least I should say that bone, since it plays so important role, it has to have ability to somehow to recover and repair itself. There are several groups of cells which are involved in this modification of bone. Each of them has a specific goal. First of all, I should say that in our life, in average, we change the material of our bones about 3 times during the life. This is a continuously working factory, very complex factory, where the old material is resorbed and the new material is created, and it happens always in our life. Since we have the several cells, the first group of cells, this is shown in this picture, is called osteocytes. These cells work as the mechanical sensors. They form a very complex 3-dimensional network. They feel mechanical loading. In fact, we don't know exactly what they feel. At least we know that they are sensitive to loading, but what is exactly the signals they measure, we don't know exactly. So these cells, osteocytes, form a very complex network, and they send the signals to the other cells, the actor cells. These cells are osteoblasts, which are the cells that build the bone tissue, and osteoclasts here, which resorb the bone. Since I have always problem to finish in time my lectures, I decided to start from the end. So I will show the results, and later on I will discuss the details and mathematical formulation. So here we have the example of some numerical calculations where the model, mathematical model of interaction between cells was applied. We analyze the piece of bone, piece of material, piece of tissue, which initially is completely homogeneous. This is the gray material. Now we apply mechanical loading. Due to this loading, the sensor cells start to sense the signal. They feel the loading and they send information to the other cells, osteoblasts and osteoclasts. These cells start to do their job. And what happened? As we see, this is the sequence of steps in time. As we see, they develop a porous material like that one. This material is very similar, this result is very similar to the real picture of real bone. This is the picture from microcity of real bone, healthy bone. So as we compare these pictures, they are very, very similar. Then, for instance, we can introduce an additional effect, for instance, osteoporosis, development of osteoporosis. And we can observe what happens. This is the next row. This is the development of osteoporosis. We see the growth of the pores and increase of the porosity. And here we have an example of osteoporotic bone. Again, very big similarity. So simple mathematical formulas result in such interesting pictures.
What induces the
Pardon?
What induces the chemical?
There are many factors. There are hormones which affect the activity of cells. As I said already, we have simultaneous activities of different cells, osteoclasts and osteoblasts. Osteoclasts resorb the bone, then come osteoblasts and they build the bone. If the osteoclasts are more active than osteoblasts, we have decrease of amount of bone. So that's osteoporosis. This is another example. It's the surgery implantation of the hip joint. This is the initial situation of the bone. This microstructure is very similar to the real one. When I performed first time the calculations and I shown this picture to medical doctors, they did not believe that this is the result of mathematical calculations. They thought that this is just the Röntgen picture which I somehow converted using Paint or some other program. But this is true. This is just pure mathematics. Then we cut this part and we place endoprosthesis here. There are three different kinds of endoprosthesis. And what happens? We can see the remodeling. The trabeculas, the small beams which are inside the bone, they change their orientation and also thickness and density. So we can compare these pictures and we can see very large differences between these three cases. So such calculation can be used, for instance, to help the planning of surgery. In fact, I already faced several such situations that doctors phone to me and say, Tomek, please make the calculations because I have a difficult case and we have the choice of several implants, so maybe from your calculations we will find some help. Okay, so it was the end of my lecture. Now let us come to the middle part. So now I will try to tell you about an approach which enables to derive adaptation law for the bone. Why do I stress derive? Because normally there are many proposals, a lot of works, hundreds of works on this subject, but usually people postulate formulas. And here we can do another approach. We make very general assumptions, and from these assumptions we can derive associated adaptation law. That means the set of formulas, equations, inequalities, which are responsible for this, what happens inside the bone with its microstructure. Okay, so of course we have to make some fundamental assumptions. So what means we have to choose what are the variables that are used to describe the microstructure of bone or density of bone or whatever we want. The orientations of these small beams, we call them trabeculas, the density of them, and so on. Then we have to find the comparison function. What is the comparison function? Comparison function is the measure which is used to compare different bones. I mean, this is something what is not well defined. We have to decide ourselves what kind of function or functional we will use. What is, according to our feeling, important for bone. For instance, one can say strength, maybe strength. Somebody else may say, or maybe stiffness. Somebody else probably will say kind of energy, or in general terms effort or cost, amount of material, or whatever. We can think about different measures. So we have to decide what measure we use to compare these bones. Then we apply the hypothesis of optimal response. What this hypothesis says? According to this hypothesis, since we consider the system which is placed in variable in time conditions, I mean the forces vary in time, biological conditions, they vary in time, chemical conditions vary in time, health, nutrition, this is something what is changing in time. So the system is not optimal itself, because the conditions are variable and it cannot switch immediately to the optimal configuration. 5 minutes, okay, so I have to speed up. So the hypothesis says that the system should follow the optimal solution as fast as possible within the constraints. Then we have to add several constraints, additional constraints. These constraints can have very different nature. Mechanical, physical, chemical, biological. The only condition is that we have to be able to describe them in mathematical terms. Then we build the functional, which is the rate of the comparison function. I mean the time derivative of comparison function. And from the necessary condition of the extremum of this functional, we get the set of equations, among them the equation which is called adaptation law. That means the equation which describes the variation of parameters which we chosen earlier, describing the microstructure and the odd shape and other characteristics we are interested in. So this is the procedure. I will not discuss this. So we consider the potato, normal potato, as in mechanics. We introduce some notation. U is the displacement vector. V is the test function. Some notation. And now we reach the point where when we have to define potential energy. We describe potential energy in this form. Now we have to calculate the time derivative of this potential energy. And it follows from our considerations that the variation of potential energy due to the with respect to the velocity of displacement as well as displacement itself, the variation is equal to 0. From these two conditions we get the equilibrium equations, and the equilibrium equations which are differentiated in time. So now our problem is to find the minimum of our functional with additional constraints. So we add additional constraints. I will not discuss these details because you cannot follow this. There are too many equations hidden somewhere inside. But anyway, finally we get such Lagrangian, such a functional, where we have the original functional cost function and a lot of constraints, also inequality constraints, which were attached here during the slack variables. So this is the functional, the general functional. From this functional, everyone can derive his own adaptation law. It's very easy because it's ready to use. You will just put functional, this functional, we just put constraints according to our needs, and we calculate the variation and have the set of equations which can be used in calculations. There is one point I want to discuss. It's just 1 minute more or 2 minutes more because it is important point. In derivation of this variation of this functional, we have to introduce Lagrange multipliers. And it follows from the deeper analysis that the Lagrange multipliers multiplied by the variation of displacement field and the velocity of displacement field represent some additional functions which are called adjoint variables, adjoint functions. These adjoint functions have a physical interpretation, what is very important because it helps in future calculations. Namely, they represent physical system as our bone, but this bone, this new bone, this adjoint bone, is submitted to different loading and different conditions. So this is important because in calculations we can use the same procedure as is used to analyze the real bone. We can use the same procedure to analyze the adjoint bone. Okay, I'm finishing. There is one more important point, namely sometimes our system is self-adjoint. For instance, if our cost function represents the global stiffness or energy, potential energy, then in such a case we have a self-adjoint problem, and adjoint system and primary system are equal to each other. This is the application of our investigations. The idea was this: we apply external excitation to the broken bone to excite cells to higher activity, to speed up the healing process. So we performed animal test, some devices. This is the external fixator stabilizer, which was placed here outside the bone, and some device to excite the vibrations. And using this device, we could speed up the healing process we can see here. After some time, this part is completely removed and the bone comes to its original state. Okay, so I finish with the conclusions. So, as I already mentioned, complexity of bone tissue is much higher than this what we face in engineering activities. Bone tissue is optimal, but we don't know what are the optimality criteria. This is what I said already. The comparison function depends on our taste. Assuming a specific optimality criterion, we can derive adaptation law, our own adaptation law. In spite of the fact that the results of numerical simulations are very similar to the real cases observed in the clinic, we have to make identification of parameters. That's important and very difficult task. And mathematical modeling is important for both, from theoretical point of view and also for practical issues. Thank you very much.
Can you also model colors together?
Yes. So we work on different things. There will be very interesting lectures today afternoon because we also consider the angiogenesis, also the healing process, different detailed aspects. Of course, we can consider any bone.
How do you characterize growth? A growth variable? Do you have a growth variable?
What do you mean, growth variable?
Bone gets larger, let's say.
I couldn't discuss this, but among the constraints, one of the constraints is responsible for the amount of bone in bone. So we can set this constraint in such a way that we have the growth.
I understood correctly, your process generates the microstructure.
Yeah.
What about the properties? Are those also, is it geometric, or are also the properties of the bone reproduced by the bone?
You mean properties, you mean mechanical characteristics in that sense, yes? Yeah, this is a good question. It depends very much on the formulation, because I discussed general formulation, but I didn't tell this, that we have to decide if we speak about microstructure or maybe density or maybe even anisotropy. So depending on the specific formulation, we can reproduce microstructure or even microstructure if we want. And of course, there is a question how to pass from the microstructure to mechanical characteristics or back from mechanical characteristics to microstructure. This is an open question. I mean, it depends what is the formulation. If I have, for instance, I assume in one of the examples, I assumed the kind of frame with thousands or millions of beams. Then we can pass somehow.
The reason I'm asking is that as you know, the mechanical properties and the microstructure depends on the age of the person.
Yeah.
It depends on the stress and also on the age.
Yes.
As far as I know, the mechanical properties are not very well defined.
Yes.
If you are able to reproduce them.
I mean, yeah. There are two aspects. The material itself changes mechanical characteristics. I mean the material which is used to build the beams, for instance. And the beams change configuration. So there are two effects, micro and say macro, or larger micro.
One question here.
Yeah, I just want to know if you consider that some noise or stochastic terms which may compete with the organization induced by the loads.
It's a difficult question because in that formulation, of course, we didn't, not of course, but I didn't introduce stochastic approach. But I think it is possible. I mean, this is possible to introduce some additional function as the constraint, one of the constraints. And then probably somehow disturb this problem. There is one thing I didn't also mention. The quality function is not just the convex function. There are many maxima and minima, local maxima and minima. So usually the bond can decide what to do on the basis of the actual information about the actual state. The bond does not know what will happen in a moment, but maybe what happened in past. I mean, it has some memory. So it follows to the local minima or maxima. So this disturbance you did mention may cause a jump to the other one.
Okay.
Okay, thank you.
Very much.